we're going to talk about in this course is predominantly related to the acquisition phase of the system lifecycle and to a lesser extent the utilisation phase. For these two major phases, we'll use the lifecycle activities that are most commonly used activities, particularly in defence and aerospace sectors. Now, the names of these activities began with the military standards and with early work by Blanchard and Fabrici, and most of the modern systems engineering and project management standards make use of these terms. In the acquisition phase, the activities are called conceptual design, preliminary design, detailed design and development, and construction and production. In the utilisation phase, the activities are operational use and system support, and these two activities are undertaken in parallel. The acquisition phase comprises the four main activities of conceptual design, preliminary design, detailed design and development, and construction and/or production. And it's this acquisition phase that we'll focus on throughout the course. Let's look at each of those activities in more detail in the coming weeks. First, is conceptual design, which represents the formal transition from the business world to the project world, so it's a very important phase. It's important because the mission statement must be able to provide a complete logical description of the system of interest so that we can acquire it in a manner that's useful to the business. It's essential that the activity finishes with a complete and comprehensive understanding of the requirements for the system so that we can ensure appropriate engagement between business managers and upper-level stakeholders. Now, this transition has three broad steps from the mission statement through to a set of system requirements. First, we develop business needs and requirements. They're articulated and confirmed by business management, and then they're elaborated by stakeholders at the business operations level into a set of stakeholder needs and requirements, or SNR. These are then elaborated further by requirements engineers into a set of system requirements, commonly called the System Requirement Specification, or the SYRS. There may be more than one system requirement specification for the entire capability system, but it's more likely that there's one SYRS for all of the constituent elements of the capability. That is, one for each of the major materials system, one for the personnel, one for support, one for training, facilities, and so on. As noted earlier, each of these constituent capability elements may be developed independently and may well be developed through separate contracts. The System Requirement Specification is the key element of what is called the functional baseline. The functional baseline represents the system-level logical architecture that describes the whats and whys of the system that meets the business and the stakeholder needs and requirements. So conceptual design ends with what's called the System Design Review, and the System Design Review, amongst many other things, finalises the initial functional baseline. It therefore provides a formalised check of the logical design. It communicates that design back to the major stakeholders. It confirms external interface and interoperability issues. It confirms the business needs and requirements, the stakeholder needs and requirements, and the system requirements, and provides a formal record of design decisions and design acceptance before we then embark on the next activity. The aim of preliminary design is to convert the functional baseline into an upper-level physical description of the system. That is, we're now going to go on and describe the hows of the system. Preliminary design is therefore the stage where the logical design is translated into the physical design, and so the focus shifts from the problem domain to the solution domain, and most likely from the customer to the contractor. The result of preliminary design is a subsystem level design known as the allocated baseline. It's called allocated because we have grouped logically the functions in the functional baseline into subsystem level physical groupings, which we call configuration items. The sum of all those configuration items is the upper level physical design of the system. At the centre of the allocated baseline are a series of development specifications, which contain the subsystem level requirements grouped by configuration item. The activity completes with the preliminary design review, the PDR. The PDR, again amongst many other things, formalises the allocated baseline. Now, it ensures that the design effort that preceded was appropriate, that it focused on the appropriate level of physical design, and it ensures the technical adequacy of the proposed solution. It also focuses on technical risk and make sure that the solution proposed in the ABL matches the functional baseline. Preliminary design also investigates the interfaces between configuration items and the compatibility of each of those configuration items. Now, the allocated baseline we developed in preliminary design is the start point for the detailed design and development, which is where traditional engineering is undertaken, to provide a complete development of the individual subsystems, the assemblies and the components that go to make up the system. At this level, we do engineering prototypes and we confirm the system design by test and evaluation. The result of the detailed design development process is the establishment of what's called the product baseline. And the product baseline, as its name implies, is about products. It's which subsystems, assemblies and components we need to then go on and build to make up the total system. As well, of course, we need to take account of the materials and the processes and the people that we need to do the manufacturing and construction. The definition of the system at this stage should be sufficiently detailed to support the commencement of the construction and production activities. The review at the end of this activity is called the critical design review. The critical design review is not critical by accident. It's the last time that the design is in paper. It's the final design review which results in the official acceptance of the design and the subsequent commencement of the construction and production. CDR evaluates the detailed design. It determines the readiness for production and construction. It ensures the design is compatible and includes a detailed understanding of all of the external and internal interfaces. The final activity within the acquisition phase then is construction and production. The components are produced in accordance with the detailed design specifications as they're laid out in the product baseline, and once they're developed, the system is ultimately constructed at the end of the activity in its final form. Then we do formal test and evaluation activities, we call them acceptance tests, which will be conducted to ensure that the final system configuration meets the requirements in the system requirement specification. Construction and/or production and the acquisition phase then ends with what's called the formal qualification review, often also called acceptance test, which provides the basis upon which the customer accepts the system from the contractor. The FQR is informed by the results of what's called AT&E, acceptance test and evaluation, which we'll talk more about later. On acceptance from the supplier, the customer then moves the system into utilisation by introducing it to service. The major activities during this phase are operational use, of course, it's the purpose for which the system was designed, and system support. System engineering activities may continue during the utilisation phase, mostly to support any modification activity that may be required. And of course, as we saw before, those modifications may be necessary to rectify performance shortfalls, to meet changing operational environments, for example, or perhaps to address some ongoing support issue to keep the system maintained. The system stays in service, hopefully for a much longer period than it took to actually acquire it, but it must end at some time, and so the system lifecycle ends with retirement of the system, which may well overlap, as we saw earlier, with the introduction into service of a replacement system. As we draw a close to our introduction to the system lifecycle, we should note that the generic system lifecycle we've discussed here is not intended to represent any particular development or acquisition model. We've presented the lifecycle activities as being undertaken sequentially because it's the best way to explain the activities and artefacts of systems engineering, particularly to those who are new. In doing so, though, we've assumed what's generally referred to as the waterfall model of system development. We have to point out early that there are, however, a number of other development approaches to implementing the activities of the system lifecycle. These are called incremental, spiral, or evolutionary acquisition models. Now, each of those has different strengths and weaknesses depending on the type of system and the type of organisation doing the development. The selection of a suitable development approach is therefore a critical activity early in the system lifecycle. But for our purposes here, for simplicity, particularly at this early part of the course, we assume the waterfall approach because it provides a nice logical sequential flow of activities and deliverables that makes it easy to explain. Additionally, it should be noted the waterfall approach is generally considered to be the basic building block of any other alternate approach, such as incremental, evolutionary and spiral, and it is still a very commonly applied development approach. For whatever reason then, a solid understanding of waterfall development is therefore very useful. Now, we discuss these issues in much more detail at the end of the course when we consider system engineering as part of the various acquisition and development approaches. Well, that completes our brief introduction to systems and to system lifecycle and completes Module 1. In the next presentation, we provide an overview of the discipline of systems engineering before delving deeper into each of the major activities. If you're interested in reading further into the topics we covered in this presentation, you may wish to read the corresponding chapters in the texts associated with the course.